Hey, welcome back. So, you know from our previous tools where we've talked about trying to find the distance to something, we've always used the parallax. And parallax is always the best way if I can possibly do it. But you know that as the star gets farther and farther away, the amount of that shift gets smaller and smaller and smaller. Eventually it gets too small to even see, even with a telescope. And that works out to be about 200 parsecs or so. Well, 200 parsecs may seem like a lot, but in reality, compared to the size of the galaxy, that's practically nothing. We're not only going to want to find the distances to things inside the galaxy, we're going to want to find the distance to things at the edge of the universe. So parallax just isn't going to work for us. We're going to have to figure out another way of finding large distances. So that's what we're going to be talking about next time, but to get ready for that, we need to introduce the concept of magnitudes. So magnitudes are related to the flux and the luminosity. It's how bright it seems to your eye versus how bright it really is. And as you know, that difference between how bright it really is and how bright it seems to your eye depends upon the distance. So we're going to use that technique to get the distance, and that's what we'll be covering in this lecture today. Let's get started. All right, so as we said, we're going to be working with magnitudes. Get your class notes out. It'll look like this, front and back of one page. It'll be tool number 22. All right, now think all the way back when we were talking about finding the luminosity, and we talked about the difference between the flux and the luminosity. So the luminosity is how bright the star really is. It's how much energy it's actually emitting each second. We measure that in units of solar luminosities, which we usually call solar lums. And remember that that's an intrinsic property of the star. It never changes. It doesn't depend upon distance. It doesn't depend upon anything. The luminosity is what it is for the star. Flux, on the other hand, is how much of that energy we actually receive at your eye here at Earth. Now remember, the energy is going out in all directions. Only a tiny little fraction of that is going to reach our eye. And the further away from the star we are, the less of that energy we're going to be able to intercept. So it depends upon our distance. And unlike solar lums, we're going to measure this in actually watts, which is the amount of power that it receives per square meter. So the new concept today is magnitudes, and they are very similar to using luminosity and using flux. So the absolute magnitude is how bright it really is. It's not how bright it seems to your eye, it's how bright that star really is out there in space. Apparent magnitude is how bright it looks to your eye. And so the apparent magnitude depends upon your distance, so it's like the flux. On the other hand, the absolute magnitude is, by definition, it's how bright that star would have, the apparent magnitude it would have if it were 10 parsecs away from Earth. We don't have to worry too much about that. But the key thing is that it's like luminosity. It's an intrinsic property that doesn't change. So anytime you see apparent magnitude, I want you to think of flux. It's brightness to your eye. Anytime you see absolute magnitude, I want you to think of luminosity. It's how bright it really is. And then, as you know, the difference between those depends strictly upon the distance. So the magnitude scale is a little bit weird, only because of its history. You want to think about magnitudes as being like a race. So the person who is fastest came in first place. The brightest magnitude then is going to be first magnitude. The person who was second fastest in the race came in second place. The star that is second most bright is going to be second magnitude. So the brightest stars then are going to have the smallest number, first magnitude, second magnitude, third magnitude. The dimmest star that you can see with your naked eye is about sixth magnitude. Now to do that, you've got to have perfect vision and absolutely dark skies to see a sixth magnitude star. So for most of us, that's just not going to happen. Here in Phoenix with the city lights, you might get, second or at best third magnitude from that. With a telescope, with the small telescopes that we have up at GCC North at the observatory, we can get around 10 to 14th magnitude, depending upon the sky conditions from that. Something like the Hubble Space Telescope can obviously go much, much fainter than that. Now, that all kind of makes sense to most people. First place is going to be the brightest. 40th place is going to be the dimmest in there, or worse. However, there are some things that are actually brighter than our first magnitude stars. And these magnitude system was created by Hipparchus, who was a Greek astronomer who lived in a couple hundred BC or so. But he could not see all of the stars that were in the sky. So there were some stars that are brighter than his first magnitude. Well, you know, astronomers are lazy. We're not going to go back through and change all our numbers on our scale from all these thousands of years of observations. So instead we say, okay, well, smaller number is brighter. So if it's brighter than first magnitude, it must be 0 magnitude. Huh? Well, just get used to it. If you see where it comes from, it starts to make a little more sense. It gets even worse. If it's brighter than 0th magnitude, it's -1 magnitude. Brighter than that would be -2 magnitude. And you know, if you take that out of context, you go negative brightness. Isn't that like ultra dark? No, it's ultra bright. But if you think about where it came from, it's faster than our first place winner. Then it starts to make a little more sense. So when we look at the stars that you see here on your, this is also on your class notes here. We've got 5 stars conveniently called star A, star B, star C, and star D. These are not real stars actually. So we're giving you the apparent magnitude and the absolute magnitude. So let's look at our characteristic chart here. And again, refer back to this. I don't want to keep both slides up at the same time. So refer back to your chart that's on your class notes. So which one is brightest as seen from Earth? A, star B, or the same brightness from Earth? So which is as seen from Earth? Is that the apparent magnitude or is that the absolute magnitude? That's going to be the apparent magnitude. So look at the apparent magnitude, looking at star A and star B, and we'll go click up one for this. Star A has an apparent magnitude of 5, star B has an apparent magnitude of 4. So which one won the race? Star B beat star A, so star B must be brighter than star A. Okay? So let's make sure that that makes sense to you. Star B has a smaller magnitude number, so it's 4th magnitude. It came in 4th place. Star A has a larger magnitude. It's 5th magnitude. It came in 5th place. So star B must be brighter than star A. All right, now you do this one. More luminosity. Which one is more luminous? Is that going to be apparent magnitude or absolute magnitude? That's going to be the absolute magnitude. So which one is more luminous? Which one has a brighter absolute magnitude, star A or star B? So we're looking at the absolute magnitude. Star A has an absolute magnitude of 4. It came in 4th place. Star B tied for 4th place. So now you see that they're actually the same luminosity. So let's think about that then. Now we've got to use some logic here. Star A is actually dimmer than star B as seen from Earth. But in reality, they're the same brightness. So the only way that's possible is if star B is brighter than it should be, if you want to think of it that way. Star B must be closer than star A. Star A is dimmer, so it must be farther away. Star B is brighter, so it must be closer, because in reality, they're the same kind of star. They're the same brightness. The only reason why star A seems dimmer is it's farther away. Star B then is closer than star A. All right, so now let's do C and D. What I want you to do is pause the video and do the same arguments for star C and star D. I'll put it up here where you can see it. Pause the video, answer all the questions on your worksheet. All right, so we're looking at star C and star D. Star C has an apparent magnitude of 0. It has an absolute magnitude of 2. Star D has an apparent magnitude of 0. It has an absolute magnitude of 0. So which one is brighter as seen from Earth? Is that going to be the apparent magnitude or the absolute magnitude? That's going to be the apparent magnitude. Well, they've got the same brightness. They've got the same apparent magnitude. So these are going to be the same brightness as seen from Earth. Which one is more luminous, star C or star D? That's going to be the absolute magnitude. Star C came in 2nd place. Star D came in 0 place. Okay, it beat the 1st place. So this is even brighter than the 1st place. So star D must be actually the brightest. It's got the brightest absolute magnitude. So that means it's got the highest luminosity. So which one must be closer to Earth? All right, well, from Earth, they seem to be the same brightness. They look the same brightness, but we know that star D is actually brighter. So if they look the same brightness to me from Earth, but star D is actually brighter, it must be way back here. So think about that. Even though it's brighter in reality, its starlight is being dimmed because of its distance. And it's being dimmed so that it's exactly equal to the light from star C, which is closer but not as bright. Do you see that? So star C must be closer to Earth than star D. Go through the logic and make sure you get this, because this is probably the only hard part about doing all this, is that whole logic of, well, wait a minute, big numbers, small numbers, and things like that. All right. So the distance modulus allows us to actually calculate a distance. Now, using this chart, you were able to figure out which one was closer, and sometimes that's enough. But a lot of times you're going to need the actual distance. And so this formula here we call the distance modulus. And little m is the apparent magnitude of the star. Big M is the absolute magnitude of the star. D, as always, is the distance in parsecs from that. Now, this, with all the logs and all this other sort of stuff, may look a little frightening. It's okay. Don't panic. It'll be okay. There are 3 steps that we need to kind of crank through this to get D, and I'm going to take you through all 3 steps with this. Okay, step 1 is always work out the fraction. So find your apparent magnitude, find your absolute magnitude, subtract them and hit equals, and then divide by 5. That gives you a number for the fraction. Step 2 is to take the antilog. That gets rid of this log. You're not going to push the log button. That's where a lot of students get confused. You're not going to push that LOG button at all. I need to do the opposite of log. Think about it. If I'm doing algebra and I've got something that's multiplied, well, I need to divide it. Now, this does not mean log times d over 10. This means log of d over 10. So to get rid of the log, I'll be left with the d over 10. Now, you got to look at your calculator to see what that analog button is. It might be INV log, it might be second function log, it might be 10x, not x 10x, that's scientific notation. It might be log minus 1. You'll have to look and see what it is. And if you can't find it, come by Live Help and we'll figure it out real quick. So you just found that number here. This is just a number. And then you hit inverse log or anti-log or 10x or whatever it is. And on some calculators, you do inverse log and then the number. Some you do the number and then inverse log. Again, it's just going to depend on your calculator and you're just going to have to figure it out. Once I do that, then that gets rid of the log and that just leaves the d over 10. So I'll have a number and that number will be equal to d over 10. So all I need to do is multiply that number by 10, the number that I got in the previous step, by 10, and that gives me the distance in parsecs. Now I will tell you this will always work. You can always just slip the decimal one place. So if I get in step 2, if I get, making this up, 5.4, then step 3 is going to be 54. If step 2 is 101.3, then step 2 is going to be 1013. Just slip it one place. But if you don't like that, if that makes you uncomfortable, it's okay, relax. You can always just do times 10 and you'll have it. All right. So let's do an example. I think that's going to be the best way to see this. So look at star A, since I can't say that. We're going to look at star A, and I want you to work this along with me on your chart. So the apparent magnitude is 5, the absolute magnitude is 4. So step 1, work out the fraction. Pause the video, go ahead and do that. All right, so step 1, work out the fraction. You put the 5 in for the little m, put the 4 in for the big M. 5 minus 4 is 1, 1 divided by 5 is 0.2. So that's our number from step 1. Doesn't mean anything yet because we're not done. For step 2, take the antilog. Now that's going to depend upon your calculator. And I will write that as 10 to the x, but I don't know how it's going to be on your calculator. And it might be that you put in the step 1 number and then do the 10 to the x. It might be 10 to the x and then put in the step 1 number. It might be log minus 1, second function log, there's any number of possibilities. So this does not mean 10 to the x times 0.2. That's not what we're saying here. We're saying take that 0.2 and then hit the 10 to the x button, or maybe it's hit the 10 to the x button and type in 0.2. All right. When you do that, you should get 1.58. So whatever you need to do on your calculator to get that. If not, you're probably going to need to get some help. So come by Live Help and we'll figure it out. All right, so then the last step, step 3, is you multiply by 10. So remember, all I have to do is move that decimal place. If you're happy with that, and it'll be 15.8. Or you can just take the 1.58 times 10 and you'll get 15.8 parsecs. So the distance to star A is 15.8 parsecs, and that's how it's done. Now, we're going to be using this technique a lot for the rest of the semester because a lot of times I can always get the apparent magnitude because I just look at the object. I might be looking at it through a telescope or I might be looking at it with my eye, but I look at it, I'm just getting the apparent magnitude because that's how bright it seems. The trick is going to be to figure out the absolute magnitude. And if I get the absolute magnitude, then boom, I've got the distance using the distance modulus. So I'm going to be teaching you some tricks for getting those absolute magnitudes as we move later on. All right, so that's actually it. That's all we have for this one. Your practice this time is going to give you another star, actually 2 or 3 of them. We're going to have you do it for star B, C, and D. We're going to have you figure out the distance to those other 3 stars that are on your original class notes. So work through it, but again, if you have any trouble at all, come into Live Help and I'll be glad to help you out. So now you know how to find the distance if you know the apparent magnitude and the absolute magnitude. Now, don't get confused. These are not really new concepts. The apparent magnitude is how bright it seems to your eye. It's like the flux. The absolute magnitude is how bright it really is. It's like the luminosity. But putting it in this form allows us to easily get the distance to anything that's out there without even knowing the parallax from that. So there'll be times when you'll know the parallax and you'll know the apparent magnitude, and then from that you can get the absolute magnitude. So you'll do some experimentation with that in the lab. But ultimately, just you've got 3 numbers. I should be able to give you any 2 of them. You should be able to find the third. All right. Next time we'll pick up on how we can use this to find the distance to very distant objects, things even in other galaxies. And so the way we've determined the distance to a lot of galaxies is the technique that we'll be bringing up on the next lecture. We'll see you then.